Yeah. In this video, I'm going to discuss about this acidity of alcohols and phenols in detail. Yes. When we look at this alcohols first, the bond which can be shown in alcohols is something like this, right? So when it can undergoes two type of cleavage actually. The bond, I mean, the alcohols can under the cleavage here or here. That means it can the bond can break in between the OH, that is OH bond breakage is occurring, or the bond can break in between C and O. If I'm taking this to be around C, I mean CH3O here. Yes. Yeah. I'm taking something, there's a methyl alcohol here. The bond can break in between C and O also. So if the bond is breaking between O and H, that means the lone pair of electrons which are present on the oxygen now will act as a nucleophile and attack on the carbocation here, resulting in the OH bond cleavage, and that means it is acting as a nucleophile. Yes, I can show you when it is acting as a nucleophile. This is how it is acting as a nucleophile here. Yes, that means it is releasing this H plus ions. That means it is acting as a nucleophile. This is one type of cleavage here where this OH bond is being cleaved. And the second type of reactions where the CO bond is being cleaved when protonated alcohols react in this manner. So this protonated alcohols means this will undergo the protonation, resulting in the formation of this protonated alcohol. This is what is protonated alcohol, and this will protonated alcohol now will act as an electrophile. Right, this one will act as electrophile now. This one is positive charge, and this Br minus, which is an electrophile here, can attack here. So as a result, which bond is being broken here? CO bond breakage. So the bond between C and O is broken here, resulting in this one, plus water. So this is acting as an protonated alcohol will acting as an electrophile here. So there's these two types of cleavage which is occurring. One is OH bond cleavage, where it is acting as a nucleophile, or CO bond cleavage, where it is acting as an electrophile. So alcohols are so called as versatile compounds because it can act both as an electrophile and also as an electrophile, depending upon the cleavage where it is taking place, whether it is OH bond cleavage or CO bond cleavage. Yes, let's understand the type of the reactions where this OH bond is being cleaved. That means it is giving the H plus. That means it is acting as what? Acid. Yes, let's understand this. When this one is, let me show the reaction with metals like sodium, potassium, or aluminium. For suppose this is reacting with sodium, what is expected here? Sodium alkoxide, right? Plus hydrogen gas. Let me balance the reaction. Yes, now it can react with alcohol. I mean, this is with metals. So it can react with aluminium also, like I'll show you the reaction with aluminium also. For example, if I'm taking tertiary butyl alcohol, right? This is tertiary, right? Tertiary butyl alcohol, when I'm reacting this with aluminium, what is formed? This is what is aluminium tertiary butoxide is being formed. Okay. Taking thrice Al plus H again, right? So let me balance the reaction. Now this one is 6 times, so 2, 6, and this will be 2 here, right? How many hydrogens here? 3. Yes. So this is aluminium tertiary butoxide, right? This is being formed. This is sodium alkoxide butoxide. And this, let me show you the reaction of phenols now. We have looked at the reactions of these alcohols. Now with phenols, so if I'm able to react with sodium, so sodium phenoxide is being formed here, right? ONA plus H2. Again, the same balancing here, right? And in addition to this, phenols can also react with sodium hydroxide, resulting in the formation of, again, the same sodium phenoxide and water. Right? So these reactions, all these reactions show that alcohols and phenols are acidic in nature. Why? Because here they're able to give H+. So alcohols and phenols are therefore acting as what? Acids. All these above reactions show that they are acids. Why? Because they are able to give H+. So they're acting as what? Bronsted acids. So Bronsted acids are those which can give proton, right? They're nothing but the proton donors. Since alcohols and phenols are able to give this H+, they are called as Bronsted acids. So I can show you the reaction of this Bronsted acids, a generalized reaction where this is a base here. So this is losing H+, this is losing H+ to base here. So BH plus OR minus, right? So this is an alkoxide here. This is what? A base. This is acid. This will be conjugate acid. This will be conjugate base. So from this reaction, it is clear that the alcohols and phenols are both acting as acids. Since because they're able to give H+, we can call them Bronsted acids. Right. So when we compare the acidity of alcohols, that is tertiary, secondary, and primary alcohols, yes, what is the order of acidity of these three types of alcohols? For example, I'm taking this primary alcohol. This is secondary alcohol, right? Yes, this is secondary alcohol. And this is tertiary alcohol. Yes. If I compare the acidity of all these three types of alcohols, which is more acidic? Yes. We can understand the acidity of this based on the electron donating effect of this R group here. We know that R here, that means alkyl group is an electron donating group, right? So electron releasing group, they are releasing the electrons towards this carbon atom. So the acidity of alcohols is totally dependent on what? The polarity of the OH bond, right? Polarity of the OH bond. The more polar the OH bond, the more acidic it will be. But as the number of the electron releasing group increases, that means they are pumping in the electrons towards this carbon atom, the polar nature will decrease. Because OH bonds become less polar because more electron density on this carbon. So there will be more electron density on this oxygen also. So it is not easy for this H+ to be lost because there is already more electron density on this oxygen. So it cannot lose this H+, but here only one R group. So the electron density on this carbon will be less. So on this also will be less, the H+ can be lost easily. That means OH bond is more polar here. So the acidic strength of alcohols depends upon the polarity of the OH bond. That means the ease with which the proton is lost. Where is it easy to lose the proton? Where there are less number of electron releasing groups. Here only one electron releasing group, here two, here three. So the acidity of primary alcohols is more than secondary than tertiary here. This is order of the acidity of primary, secondary, and tertiary alcohols. Right? So polarity is directly proportional to the acidity. The more polar, the more acidic. The more number of electron releasing groups is inversely proportional to the number of electron releasing groups or electron donating groups. right? More number of electron donating groups, the less acidic it is, or less number of electron donating groups, more acidic. So this is what is the acidity of alcohols. Yes. Now, which is more acidic, alcohols or water? Let's understand this. Yes, when I show you this reaction, it can be better understood. Yes, when we take this alkoxide ion, reaction with water, this clearly shows this is forming alcohol plus OH minus, this is hydroxide. Right? This is a base, this is an acid, this is a conjugate acid, and this is a conjugate base. Now, when we look at this reaction, the water is losing the H plus here. The water is a proton donor, and this alkoxide ion is a proton acceptor. From this reaction, we can clearly understand that this water is a better proton donor when compared to that of this alcohol, which means that water is more acidic than alcohol. So water is more acidic than alcohol. Because from the above reaction, we can see that the water is a better proton donor than alcohol. Right. Now, let's compare the acidity of phenols with alcohols. So which is more acidic, alcohols or phenols? Let's understand this. Yes. If I'm taking, for example, not for example, this is a generalized reaction. If it's an alcohol, so how is ionization taking place here in order to form this? In order for this to lost H plus is, yeah, this is the reaction. And for phenols, yeah, this is the phenols reaction. Yes. Right? Yes. Here, the alcohol is ionizing to give an alkoxide ion and H plus. Here, phenoxide ion and H plus. Yes, here, which is more acidic is dependent upon two factors. Yes, either alcohols or phenols. Yes, the first one, in alcohols, the oxygen is attached to sp3 hybridized carbon atom. Right, so I'm taking this as CH3 here maybe. Here it is attached to sp2 hybridized carbon atom. Right, so we know that sp2 hybridized carbon atom is more electronegative when sp3 hybridized carbon atom, electronegativity. Because it has more of S character. That means it's more, the electrons of this is more closer towards the nucleus of sp2 hybridized carbon atom when compared to sp3 hybridized carbon atom. Right? So since sp2 hybridized carbon atom is more electronegative than sp3 hybridized carbon atom, this bond pair of electrons, that means electrons in between C and O, is more closer towards this carbon atom in phenols when compared to that of the shared pair of electrons between C and O in alcohols. That means here the electrons are closer towards this carbon when compared to that of the electrons towards this carbon. So as a result, which is more polar now? This is more polar because this is more closer towards this carbon. As a result, oxygen will easily tend to draw the electrons from hydrogen, and this will be lost as proton. Right? So depending upon the electronegativity, we can say that OH bond in alcohols is more polar when compared to that of the OH bond in alcohols, phenols, alcohols. So since acidity is dependent on the polarity of the OH bond, phenols are more acidic than alcohols. This is the first reason. And when we come to the second reason, yes, when we come to the second reason, if I said the alkoxide ion is formed in the case of ionization of alcohols, and the phenoxide ion is being formed in phenols, right? So if you look at the stabilization here, OR minus is not resonance stabilized, but this phenoxide ion is resonance stabilized. So if you look at the resonance stabilization in phenoxide ion, this is what is the resonance stabilization. These are what the resonance structures of phenoxide ion. And these are the resonance structures which are seen in phenol. So since alkoxide ion does not have resonance structure, so phenoxide ion is more stable than alkoxide ion. So it is easily formed. So phenoxide ion is easily formed than OR minus, that is alkoxide ion, because phenoxide ion is resonance stabilized. So this is a second reason why these phenols are more acidic than alcohols. Right? Since there is a resonance stabilization which is possible in phenoxide ion, these are the resonance structures, but in alkoxide ion, no such resonance stabilization is there. So phenoxide ion can be formed more easily than alkoxide ion. So phenols are more acidic. That means equilibrium shift towards the right side when compared to that of these alcohols. Yeah, no doubt these resonance structures are present in phenols also. Yeah, this phenols, yes, this is a phenol. Yeah. Phenols also, this resonance stabilization is possible. But when we look at the resonance structures here, see, there is a charge separation in them. There's a positive charge on this, right? And negative charge on the ring. So in all these resonance structures here, we can see the charge separation here. But in phenoxide ion, there is no charge separation, only charge delocalization we'll see. See, the charge is delocalized over the entire ring. Here there is a charge separation, here is the delocalization here. So we know that the resonance structures with charge delocalization or without charge separation are more stable when compared to that of the resonance structures where there is charge separation. So phenoxide ion is more stable than phenol. If you look at the resonance structures, since there is the charge separation in the resonance structures of phenol, phenoxide ion, there is no such charge separation. Phenoxide ion is more stable than phenol. That is why the phenoxide ion is more stable than phenol and also the alkoxide ion. This is the two reasons why we can say that phenols are more acidic than alcohols. First reason is based on the hybridization, and second reason is based on what resonance structures or resonance stabilization of alkoxide and phenoxide ions. So here, resonance, two reasons why these phenols are more acidic than alcohols. One is hybridization, and the second one is based on the resonance stabilization of alkoxide and phenoxide ions. So now let's look at the resonance, acidity of substituted phenols here. Yes, if you look at the pK values of the substituted phenols, this is nitro substitution, right? This is phenol and this is orthonitrophenol. Right. So this nitro, we know that it's electron withdrawing group. So if electron withdrawing groups are present on this phenol ring, this will increase acidity. Why? Because it will increase the polar nature of this OH bond. This OH bond becomes more polar. We know that if it is more polar, it is more acidic. So it will withdraw the electron density from the ring. As a result, the electron density on the oxygen also reduced. So it will in turn will draw the density from this H, and this H plus can be lost easily. So electron withdrawing groups are, if electron withdrawing groups are present on the phenol, they are more acidic. And if they are present at ortho and para position, the effect is more pronounced, because if you look at the resonance structures of this phenoxide or phenol, the negative charge is present at ortho and para positions. So this can be effectively delocalized by this nitro group if they are present at ortho and para positions. That is why if we look at this, ortho and para are more acidic. This pKa is inversely proportional to the acidity. The less the pKa, the more acidic it is. So first comes para, then comes ortho, then comes metanitrophenol. Then it is the phenol. So that is why electron withdrawing groups are present on the phenol ring. They are more acidic when compared to that of the phenols. That's why nitrophenols are more acidic than phenol. Then comes crisols. So what is crisols here? This is crisol. So CH3 is electron donating groups. So they are donating the electron density in the ring. So the OH bond becomes less polar. That means less acidic. That means H plus cannot be lost easily. That is why this ortho meta para crisols are less acidic than phenols here. Right? So nitrophenols are more acidic than phenol. Then comes this crisols. And first comes meta, then ortho and para, then ethanol. So I can write here, so para nitrophenol is more acidic than ortho nitrophenol. Then comes meta. Then comes phenol. Then comes crisols in the order. Then comes the alcohols. Yes, this is the acidity of, comparing the acidity of alcohols and phenols. If you like this, please do like, share, and subscribe my channel. And coachings are also offered from Isha Chem Academy. Yes, and the details have been given in the description box below.